All right, hello everyone. Welcome back. This is our second discussion of Module 2. So in this discussion, we're going to talk a little bit about these greenhouse gases in a little bit more detail with this. So all of you should have the outline hopefully in front of you. And I want to step back for a minute and just talk a little bit about the very first assignment I asked you guys to do. Some of you, of course, thought it was kind of corny, or, how can you argue that this global warming and climate change is necessarily a good thing? And I want to point out to you is that when we first started really talking about this a lot in science and in public in the 1980s is where a lot of the conversation really started to pick up. There were some folks, hydrologists, farmers, that sort of made the argument saying, hey, all we do is hear about doom and gloom on, this increase of greenhouse gases and climate change and global warming. Is this necessarily always a bad thing? Could it actually increase things like the availability of fresh water? Less than 1% of all water out there is actually fresh water, but all human beings on this planet need that fresh water. So they were trying to make some argument about that. Hey, maybe this is not such a bad thing, generally speaking, because this will increase our access to fresh water. That might be a bit of a stretch, but okay. Then there were some within sort of the soil industry, the farming industry, and said, hey, globally speaking, this might also increase our growing seasons. Is that a bad thing? So anyway, so I want to point out to you, and why I have on the handout here on the lecture outline, sort of, the greenhouse gases argument for the increase it. And again, you still might think that's a bunch of hooey, and I understand that. I'm not a real advocate for it, but I just think it's important just to have you sort of address this and point out to you that there actually have been some people saying that, hey, this is not necessarily a bad thing. Well, I guess only time will tell whether this is a good or bad thing or not, but I just wanted to bring that up to you. Okay, so let's go ahead and let's dive into this, and I'll bring the handout up. All right, so again, you should have that in front of you. But anyway, this is kind of where I'm going with this. So I'd like to sort of spend a little bit of time with you guys. And let's sort of talk about this in no particular order. I'm just kind of running down the line here in terms of some of these greenhouse gases. Well, carbon dioxide levels, of course, have always fluctuated. And I want to point out to you that over the last, say, 200 to 300 years, there has been the discussion that CO2 levels have actually increased by about 30%. You might say, okay, if that number is actually true, all right, where does a lot of this actually come from? Well, we know that there are natural processes that create carbon dioxide. We also know that there are anthropogenic, and that means human causes, all right, with this. But I want to sort of spend a few minutes just talking a little bit about some of this stuff when it comes to actually CO2 and where we get a lot of this from, okay? And so in no particular order with this, I'd like to just sort of show you sort of the growth of CO2 levels that we've seen around the globe. All right, so this comes from, again, another NOAA chart here with this. And if you sort of look at this, of course, you see on the left-hand column here sort of CO2 emissions, all right? And then, of course, the timeline going back here towards the 1750s. Now, if you look at this, of course, we'll see that from 1750s up here to the mid-19th century, okay, 1843, you see there's not a lot going on here. Now, is that because there's a lack of industry? Maybe so. There's obviously no automobiles. Also, we don't really see the growth in human population. We really don't see the growth of human population start to take off until the 1800s, okay, and make our way up. Okay, so if you look at this, you'll notice as we make our way from 1843, and this ends here at 2010, but of course you kind of get the idea this trend is continuing, you'll notice this monumental rise of global carbon emissions per capita. All right, so we've seen a phenomenal rise in this that has taken place. Now, there are natural ways that carbon dioxide is added, things like volcanoes, okay? So let me come down here to one of my images here, and we'll look at this, okay? So this is a plate tectonic map, okay? This is sort of a geologic map, but I just want you to look at this. So these red hash marks here, of course, are earthquakes, and we're not talking about that, all right? But we're looking at these black triangles, and you can see this all along the west coast of the Americas and the east coast of Asia, making its way around. You see it in Africa and sort of splattered elsewhere. Volcanoes, there's nothing you and I can do about that. But when a volcano erupts, it releases things like tephra. This is dust, sand, rocks, whatever. That stuff sort of settles over time. But as we all know, is that volcanoes also emit gases. Those gases we, of course, don't see, like we see dust in the atmosphere. Those gases linger much longer. And those gases have a real impact on our atmosphere. It might have a much bigger impact in the area that the volcano erupted. But remember, those gases don't remain static, meaning those gases are released, the jet stream, winds, global wind patterns will sort of push those along. So we know we have things like that. We also know just by you and I breathing, okay, we breathe in, we exhale the carbon dioxide. So we see things like that as well, okay? All right, so we know that these things are very, very important with us. And we know that a lot of CO2 is created naturally. CO2 is also very, very important for us, as I said, in terms of photosynthesis, all right, and the creation of oxygen. Deforestation is very important in this topic as well. And a little bit later on in the semester, we'll talk more about this. But what happens here, of course, is that many people don't sort of think about this, but CO2 levels over the course of the year are like a real big roller coaster. So if I take trees, deciduous trees, trees that have leaves, that lose their leaves in the winter. In the summer, they're able to absorb a lot more of this carbon dioxide through their leaves. So they take this in. Obviously, if they're taking this in, the CO2 levels drop. But what happens in the winter when they lose their leaves? So those leaves will fall. They don't take in quite the CO2, all right, as they did in the summer. So we tend to see spikes in this, all right? So it's the same thing like air quality issues. It's not that ozone isn't there in the summer, we just see it more prevalent in the winter, things like that, okay? It becomes more visible to us. All right, so we know that there are natural causes of CO2, and then of course there are man-made sources of CO2. Things like agriculture, things like transportation, the burning of fossil fuels, okay? And we have a whole section here, we're gonna talk about fossil fuels with this. Now, one thing that becomes very important in our discussion with this, I'd like to show you here something that is important in all sciences. So those of you that are majoring in some of the sciences, in your career, you'll probably deal with what are called proxies. And one way that we can actually see this is that the coring of ice has become a very important part of this whole discussion of global warming and climate change, atmospheric sciences in general. So a lot of the data that we get, all right, on CO2, and not all of it, of course, but a lot of it that we get it through places like Antarctica and ice coring. This is called a proxy. Well, the reason why Antarctica is so important to us is that one is it's considered to be sort of unbiased data. Why? Because there are no permanent human populations there. There is no industry to speak of. There is no, there are no freeways. There are no automobiles. There's no industrialization. And so when we look at this, we go to these sort of neutral sites and we core this and say, okay, what are we actually seeing in these proxies? And what will happen, so you'll see here, we're coring this ice and you see the big column of ice that comes out. The ice then is sort of taken, it's measured, it's studied. And what a lot of science is looking for is they're looking for things like air bubbles. This is a good indicator of carbon dioxide levels. And so what you can do is you can sort of slice and dice this ice and you could go through geologic time to sort of look at this. Where are periods where we see the trapping of more CO2 some years and some time frames than in others, okay? And so, as I said to you, over the past 200 to 300 years, we've actually seen a significant rise in these ice cores coming out of Antarctica at about 30% rate, okay? So we do know that CO2 levels are actually rising. The last thing that I'd like to say about CO2 with this for our purposes is that where does a lot of the CO2 end up? About half of all of the carbon dioxide out there is actually absorbed by the oceans. So once again, you know, if CO2 traps heat, we said that it does trap heat, and it has a longer life in CO2, well, that's only adding to the warmth of the oceans as well, okay? All right, so let's continue on with this. So we know that the sources, you know, beyond natural volcanoes, things of that nature, we do know that things like industry, transportation plays a very, very significant role in this. Okay, so let's move on. Let's talk about methane. All right, so methane has an incredible ability to hold heat. However, its life is not as long as CO2, meaning that it's sort of used up or it's released or something to that effect, okay? And if you take a look at this chart here that I have, all right, in blue, these are considered to be natural sources, and these are not all of them, all right, natural sources of methane. All right, so you see these things here. And so a lot of the methane that we're dealing with today really is sort of looked upon as sort of being more human involved. Now, I want to point out something to you that I sort of question with this. You and I can't do a whole lot about the methane that is created by cattle, okay? So I sort of question this one right here. Cattle, if you're not familiar with this, and I don't need to get into detail with this, cattle are a major source of methane through the passing of gas. They have a very poor digestive system. They have a very hard time digesting a lot of the grasses and the hays and things like that that they eat. And so therefore they have some digestive problems, and you can sort of fill in the blanks with that one. Well, if you're saying that this is man-caused, well, maybe it's what we're feeding the cattle, I don't know what. But nonetheless, okay, this one here, I think you could kind of argue could also be sort of a natural process as well. But what I'd really like for you to take a look at here with this is that, of course, we see things like mining, all right? We see fermentation. Rice is actually the most grown crop in the world. It obviously dominates in places like Asia. I'm not trying to be stereotypical, but rice is consumed in phenomenal amounts in Asia. So we see this, all right? So you do see that coming around here. A lot of our methane challenges are considered to be more anthropogenic. And what that means, of course, is that they're human created. And I want you to understand that, you know, we can debate this stuff all day, but nonetheless, we do know that it is, you know, humans play a rather significant role in this. Landfills, I would say to you, are getting much better. Historically, they were a huge source of methane. But with improved sort of waste disposal techniques and stuff like that, that's coming down a little bit. Okay, all right. So if we continue on down the line, we look at things like ozone. So without getting too much more involved in this, and again, I don't mean to belabor the point with this, we do have good ozone and we do have bad ozone. And so we know that there's sort of the chipping away, all right, of that ozone layer that's mostly from CFCs. But do understand what's happening here, of course, is that the ozone that we're creating as human beings here with respect to this, mostly through transportation, not exclusively, but that's the big one. This is a photochemical reaction. And so, guys, if you look at this image here I have, so we have pollution. That pollution is generated predominantly, not exclusively, from things like transportation. It could be also from energy production, whatever. When it mingles with heat and also sunlight, it goes through a chemical reaction. This is called photochemical reaction. What happens with this, of course, is that I go from something like O2, oxygen, to O3, which is ozone. So again, this is the stuff that is getting trapped, and it's what is called ground level ozone. And this ozone, of course, sort of the pollution, the heat is trapped, all right, with this. So this is obviously a contributor to our discussion as well. All right, the next item of business is nitrous oxide, okay? And I want you to sort of look at this, and as I point out to you that even though this is just a US map, this sort of parallels what we see around the globe. It's not that you and I in the US create more of this or less of it. The sources all tend to be relatively the same around the globe. Nitrous oxide is like a sponge. It does hold a lot of heat, okay? And so when we look at this, take a look at just some of the sources of this. So around the globe, all right, much like what you see here in the United States, okay, agriculture plays a very significant role with this. These are different soil management, pesticides, fertilizers, things of that nature, all right, that we actually see. And then if you continue on around, you'll notice that we go to things like power plants, all right. Again, manure is part of this, transportation plays a role in this. But our big contributor I just want to point out to is agriculture. Now, if we look around the world with this, even though in this country, there's only a very small percentage of us within the agriculture or ranching industry. You know, 150 years ago, that's what dominated. Today, that's no longer the case. But remember, if I look around the globe today, most people around the world make their living or survive from agriculture or ranching. So this is not going away anytime soon, but for our purposes, that agriculture plays a significant role in this. And nitrous oxide comes from, not exclusively, from a lot of agriculture. And this is a rather significant source of holding heat, okay? Next is something that became a hot topic of discussion in the 1970s in this country. And that was sort of the increase of chlorofluorocarbons, or what are called CFCs, which is a little bit easier. And it became a big issue in 1974. The federal government, the US federal government, was sort of looking at this and saying, you know, we think we have a problem here, not only in this country, but what we see around the world. And we believe that CFCs are playing a role with this. So, long story short, chlorofluorocarbons are coming from things like aerosols, coming from things like Freon. Freon is, of course, what you have in your car air conditioner. It's what you have in your refrigerator or your freezer, okay? These are believed to have a significant role of sort of eating away or chipping away at the ozone layer, the good ozone, okay? So I know that this image is not as clear, all right? But what happens if this is true, and we start to see the erosion of the ozone layer? Well, there's a couple things, of course, that happen with this. As you notice that ozone layer, which is our big filter for harmful ultraviolet rays, things of that nature, sort of, you know, erodes, and it allows more of this ultraviolet, more heat, more energy to reach the Earth's surface, okay? And so what's happening here with respect to this is that you see that erosion. Well, we know that perhaps you see rises in things like skin cancer. By the way, places like in Oceania, that would be Australia, New Zealand and stuff, the big killer in Australia is actually melanoma. And this is where historically we've seen sort of the erosion, if you will, where we see a lot of the thinning of the ozone layer. The other thing that I want to point out to you is that this has also been a problem in Eastern Europe. And the argument was with this is that under communism, and I'm not trying to make a political statement here, I just want to point out to you, there was really no regulation. There was no regulation of burning of fossil fuels, things of that nature. And so there was a tremendous amount of burning of fossil fuels, and we started to see a lot of acid deposition problems, a lot of acid rain in many parts of Europe. And some of the argument is that we've also seen the erosion of some of the ozone layer in the Eastern Europe area as well. Okay, so we know that CFCs have played a role in this to a certain degree. All right, and last but not least, of course, that I want to point out to you is the one that is the most abundant for us, and that, of course, is the water vapor. Okay. Now, many of you are probably familiar with the hydrologic cycle. This is a closed system, meaning that water is always going to be there in a solid, liquid, or gas. But the thing of it is, in this hydrologic cycle, is that we sort of see this, and what happens here is that as water falls and as it evaporates, it's sort of redistributed around the globe, okay? And so what this actually means is that human beings have very little role in this. You know, this is just a natural process that takes place. And so we do know that even though water has a very, very short life cycle with this, okay, what I mean by that is that, of course, that evaporation, as you notice here, will rise up. It will turn into a cloud, it rains, and it's converted from a gas back to a liquid. But remember, water is a major source of heat. It holds the heat, all right, with this. The other thing I want you guys to take a look at, you also have a process called evapotranspiration. This is different than evaporation. Evapotranspiration is the evaporation of water through leaf pores. All right, so we know that we see this evaporation through vegetation as well, and that's just adding to it with this. So I want to point out is that, you know, if temperatures are rising, and there's every indication, obviously, that there is, that you and I are anticipated to see a rise in evaporation rates, okay? Now, why is this important? This is part of the conclusion that comes from NASA, from NOAA, the World Meteorological Organization, is that if we look at this, with temperatures rising, we know that we can anticipate more melting, all right, of ice sheets, of glaciers. That means there's more liquid water. That liquid water then becomes susceptible to evaporation, and we see more water vapor in the atmosphere. So what the conclusion is with some of these from the WMO, NOAA, all right, people like this from NASA say, look at, what you'll probably see is that you will potentially see a rise of more than 8 to 10% more moisture in the atmosphere with every 1 degree Fahrenheit rise in temperature. Now, what this also means, though, is those places that are already wet are anticipated to become even wetter. In a place like Nevada, the driest state in the country, I don't think that means that all of a sudden we're going to become very wet, all right? But what it means is those places that are wetter will only become even more wet. And I can tell you the bulk of the world's population lives in wet climates. Think of Southeast Asia. Think along the tropical regions. Even in this country, 2/3 of the US population, folks, lives east of the Mississippi River. There's not a lot of us out west, comparatively speaking. Yes, you have California that's got, you know, quite a few people. But if you look at the population distribution, most people live in the eastern United States. The other thing to keep in mind, and you're going to be doing a little bit of research on this later on, is that most people around the world live relatively close to the coast. Well, if you've never been to a place like Houston or New Orleans or Mobile, Alabama, or Miami, Florida, these places are at sea level or below. Go to New Orleans and you're actually below sea level. Now, these places that if the oceans rise, all right, this is going to pose a significant challenge to people around the world. Okay, and again, a little bit later on in the semester, you're going to be looking at this in more detail. So all of these greenhouse gases play a role in our discussion here. Some may play a little bit bigger role than others. But I think it's important for you to understand is that water vapor is our most abundant, and it has a phenomenal ability to hold heat. It does have a shorter life cycle. And because it goes from a gas to a liquid, back to a gas, back to a liquid, all right, and we're seeing the recession of glaciers and ice sheets around the world, we can anticipate sea level rise. When we get to the sea level rise discussion of this, it takes very little sea level rise to actually consume a fair chunk of land, okay? All right, so I'm gonna leave it at that. All right, so again, if you have any questions or comments with this, please let me know, okay? I will check back with you with just one more very brief discussion on this module. Okay, take care, have a good day, bye.